have studied already how to make operation between matrices. Now let's start studying how to make operation between the elements in the matrix. So the operation I'm going to speak about are the elementary row operations. There are three types of row operations that can be performed in the row of a matrix. If a matrix B is obtained from matrix A by performing row operations, we say that A is row equivalent to B. And we are going to write in this way A, and we are going to read it in this way. A is row equivalent to B. There are three types of row operations, and the first that I'm going to speak about is the row swap. Switching two rows of a matrix. That's what we are going to do. If we switch row I and row K, we are going to write Ri and this double arrow Rk. So anytime that I see beside a matrix this operation, it means that I'm going to switch Ri, row I, and row K. For example, if A is this matrix that have these elements A sub 1, 1, A sub 1, 2 until A sub 1 n in the first row, and we have a similar row here, let's call it row I, and with more rows we have another row K, and the last row at the end, in this case we have a matrix that have m rows, and we see beside the matrix the operation I interchange with Rk, so it means that we are going to switch these two rows. So when we type the matrix, the result of making this operation is just switching these two rows here. The matrix that result will be row equivalent, so I can write here row equivalent, and the matrix that result has in the place where was row I is now row K. And in the place what was before the row K is now row I. So this operation just leave the other rows exactly as they are and just change these two rows. Just switch these two rows. This is the first operation we can make in the row of a matrix. The second one is what we call row multiplication. What we do is multiplying a row by a scalar, so by a real number. So if we multiply row I by the scalar lambda, for example, what we are going to write is lambda Ri will be substituting Ri. So we use this double arrow to symbolize that the row I will be changed by the same row I, but now multiplied by lambda. So for example, if we have a matrix A like this, so we have all similar to the previous one, but we are going to be focusing in the row I. And if we write beside this matrix this operation, it means that the row I, so this row, will be multiplied by lambda. So we're going to change this row, the rest of the matrix will stay the same. So the answer will be a matrix like this. So they have the same rows, all the rows are the same, but in the row I will appear multiplied by the scalar lambda. So that will be making this operation. Obviously, the matrix that we obtain is row equivalent to the previous one. And finally, the third operation is called row addition. So what we are going to do is replacing one row by the sum of itself, so the same row, and a multiple of another row. So we are going to write in this way, Ri plus lambda another row. So the row I will be to the row I will be added lambda times, so on a scalar lambda in this case, could be 5, could be 6, whatever is scalar, multiplied by Rk. And that will be substituting to the previous Ri. So it will be the same Ri that you see, plus another row multiplied by lambda, by the multiple of another row. For example, if we have again the same matrix, and we have one row that is the row I, another row, the row K, and we see beside this the operation Ri plus lambda Rk will be substituting Ri. It means that this row, that is the row I, will be substituting, instead of this, will appear the same row plus lambda times the row K. So the answer will be a matrix that have the same rows, except that the row I will be substituted by the same row I plus lambda times the elements in row K. For example, the first element will be the first element of row I plus lambda times the element in the row K, the respective element in row K. The second element of this row will be the second element plus lambda times the second element of row K. And so on. Every element will be substituted by the same element plus lambda times the corresponding element in row K. That will be the operation, the row addition. So we'll be adding to a row another row that has been multiplied by a number. Let's see some examples. Assume that we have this matrix A equal minus 1, 2, 7, 2, 0, negative 5, etc. So this is a 4 by 3 matrix. And we see beside this matrix the operation R3, R1. So means that we are going to switch R3 and R1. We are going to swap these two rows. So the equivalent matrix will be another matrix in which the other rows remains the same. For example, the second row remains the same. The last row, minus 1, 0, 3, remains the same. But in the first row, we're going to see that was before row 3. So here will be minus 1, 2, 7. And in the first row, I'm going to type 4, 4, minus 6. So that will be the new matrix. And this matrix will be row equivalent to the previous one. This is an example of a row swap. An example of row multiplication could be something like this. We have a matrix, let's see the same matrix, and assume that beside the matrix we see 3R4 is going to substitute R4. So it means that this R4 will be substituting by the same row multiplied by 3. So the answer will be a matrix in which the other rows remains the same. The first row doesn't change, the second row doesn't change, the third row doesn't change, but in the last row, instead of minus 1, we're going to have minus 3. We're going to multiply by 3. In here will be 3 times 0 is 0, and here will be 3 times 3, 9. So it will be minus 3, 0, 9, the elements in this row, and that will be the new matrix. This matrix is row equivalent to the first one. Finally, the last one, row addition. Assume, for example, that we have the same matrix, minus 1, 2, 7, etc. And we see beside this the operation R1 minus 2R4 are going to substitute R1. What does it mean? That this row is going to change. Row 1 is going to change. And what will be changed? It will be changing by the same row minus 2 times row number 4. So it means that the other rows, second and third, doesn't change, and the fourth row doesn't change. The only row that's going to change is R1. And I say substituting R1. It means this is the only row that is going to change. The only operation when the two rows change is in the first one, when we are actually switching the two rows. But in this case, is the only R1 is going to change. So this will be row equivalent to 2, 0, minus 5. There is no change in the second row. There is no change in the third row. There is no change in the fourth row, but the first row will be the same first row minus 2 times the 4. So it will be minus 1 minus 2 are 4, minus 2 times minus 1. That will be actually plus 2. Will be minus 1 plus 2. So it will be 1. 2 plus minus 2, 0 times 0. 2 times 0 is 0, so it will be 2 minus 0 is 2. And here, so there is no change in here. And this will be 7 minus 2 times 3. It will be 7 plus minus 2 times 3. So it will be 7 minus 2 times 3. So 7 minus 6. 7 minus 6 is 1. So the first row will be 1, 2, 1, and close the bracket. So this will be the new row. We have changed the first row that was minus 2, minus 1 to 7 by a new row that was the first one plus minus 2 times R4. So let's define the concept of elementary matrix. An elementary matrix is one that has been obtained by performing an elementary row operations to an identity matrix. So there are 3 types of elementary matrix, one for each elementary row operation. So it will be 1 for the row swap, for sure. So, and how is going to be? It will be 1 in which we have performed the row swap to an identity matrix. For example, if we have this matrix, this is an identity matrix of 4 by 4. Remember, the identity is a diagonal matrix in which all the elements of the diagonals are 1. So it will be a square matrix, and in this case is the identity matrix of size 4. If we make a row swap to this, what we're going to obtain is an elementary matrix. And assume that we made this. So we have switched the row 2 and row 4, if you notice. The row 4 now appears as row 2, and the row 2 appears now in the row 4 of this matrix. This, I'm gonna call it here elementary matrix number 1, because it's my first example. But this is just an example of an elementary matrix. This matrix has been obtained by switching the second and fourth row of the 4 by 4 identity matrix. So this will be an example of an elementary matrix. Another example will be in which we have made a row multiplication. For example, if we have this identity matrix, and I notice this is the 3 by 3 identity matrix, we can make any row operation, and what we obtain is going to be an elementary matrix. For example, if we multiply this third row by negative 9, so we have here an elementary matrix. Why? Because this one is a matrix that has been obtained by multiplying row 3 of the identity, 3 by 3 identity, multiplying this row by negative 9. So this is an example of an elementary matrix. So it will be an infinite number of examples that I can get from here. This is one of them. Obviously, it will be elementary matrix in which we make to the identity a row addition. For example, again, if we have this E4, so the identity 4 by 4, and we make a row addition, for example, what happens if we, to the first row, we add 5 times the row number 3 to the first row. So what we're going to have is that the element here will be 5. You see that? That is, if you multiply this by 5 and add it to the first row, we're going to obtain a matrix like this. So the first row have been substituted by itself plus 5 times R3. So it means this matrix is an elementary matrix because it has been obtained by adding to the first row of the 4 by 4 identity matrix the third row multiplied by 5. So any elementary matrix is like this, switching two rows of the identity matrix, or maybe in which one of the one appears multiplied by a number. So you have a diagonal matrix in which there is only one number that is different than 1. So this is an elementary matrix because has been the identity multiply one row by a number. Obviously the other numbers of the row will be 0 because multiplying by 0 doesn't change the other numbers. But this number, the 1, has been changed by this -9. Or sometimes we have a matrix in which all the elements in the diagonal is 1, but one of the 0 is a number different than 0. So it means that it was an identity matrix in which we have adding to one of the row another row multiplied by a number. So it's easy to recognize a elementary matrix. It's just seeing if there is like identity but one of the 0 is not 0. This is for sure an elementary matrix. Or a matrix in which one of the 1 is not 1 but a number different than 1 and different than 0. And another matrix in which we have switched two of the 1s. For example, this 1 should be here in the 4th element of this row and this 1 should be here. So we recognize immediately that this is an elementary matrix. One important result related to elementary matrix is the following. Multiplying any matrix on the left-hand side by an elementary matrix produces the same result as performing the equivalent row operation. So it means the operation that has produced the elementary matrix from the identity. For example, assume that we have this matrix -1, 2, 7, 2, 0, -5, 4, 4, -6, -3, 0, 9, and we multiply this by an elementary matrix. Let's see, multiply by this matrix. Remember how we term this matrix? Switching the second and fourth row of the identity. If we multiply this matrix by this elementary matrix by this A, we multiply left side. So put it at the left side. Remember that the operation multiplication in matrix is not commutative. So we put the elementary matrix at the left. So we are going to multiply this matrix by this, but remember, multiplying a matrix by another matrix is multiplying the rows of the first matrix by the column of the second. So it will be 1, 0, 0, 0 multiplied by -1, 2, 4, -3. If we multiply this 1, multiply this -1, this will be 1 times -1, -1. 0 times 2 is 0, 0 times 4 is 0, 0 times -3 is 0. So multiplying this row by this column produce only -1, because this is the only product different than 0, 1 times -1. So this number is -1. So let's open bracket, and when I multiply first row, first column, the answer is just -1. The same number that we have at the beginning. If we multiply first row, second column, to see the number in the first row, second column of the product, it will be 1 times 2, 2. But the other product will be 0. So it will be 2 plus 0 plus 0 plus 0. So it will be 2. So it doesn't change this 2. If we multiply the first row by the last column, so the third column in the second matrix, it will be 1 times 7 will be 7. The others will be 0. So I notice that when I multiply the first row times the other matrix, the first row doesn't change. But when I multiply the second row, remember, in the second row will be second row of the first matrix, first column of the second matrix. So it will be 0 times -1, 0. 0 times -2, 0. 0 times 4, 0. 1 times -3 will be -3. So in this case, when I add together 0 plus 0 plus 0 -3, the answer will be -3. Again, let's multiply second row, second column. 0 times 2, 0. 0 times 0, 0. 0 times 4, 0. But 1 times 0, oh, 0. So in this case, all the products were 0. And then go to the last one. This row times this column. You notice that the answer will be 9. So Now the fourth row appears now as a second row. And now if we multiply this 0, 0, 1, 0 by the matrix again, 0, 0, 1, 0 by this, and you notice that the answer will be 4. The other terms will be 0. So this will be 4. We multiplying this by the second column, the answer will be 4, because this 4 is the one that will be multiplying this one. The other numbers in their column will be multiplied by 0. So multiplying this row by this column produce number 4. And multiplying this row by the third column produce negative 6. So there is no change in this. But the last row, because we have interchanged this, when I multiply second row by the matrix, this one is going to multiply these two. You see that? 0 times negative 1, 1 times 2, 0 times 4, plus 0 times minus 3, the answer will be 1 times 2 equal 2. So this fourth row multiplied by the second, the answer will be 0. And this fourth row multiplied by the third column, the answer will be, when you multiply, it will be this negative 5. So this will be. So it means that if we multiply this elementary matrix by the matrix, the answer, I know, it will be a matrix in which we have switched the second and fourth rows. And why? Because we multiply an elementary matrix that was obtained by this operation. So the operation that we have made in the elementary matrix, it will be the same operation that we are going to do with this multiplication in the matrix. So that means if we multiply on the left hand side by an elementary matrix produces the same result as performing the equivalent row operation. Let's multiply the matrix A by E1 produces the same effect of the row operation. Multiplying by an elementary matrix is actually make a row operation. Let's see another example. Imagine that we have this E2. You notice that this is an elementary matrix because this is the identity in which we have multiplied by 2 the second row. So if we multiply this by the matrix, the same matrix that we had before, what we are going to notice is that it's going to be the same matrix, but the third row will be multiplied by 2, exactly as it was done in the identity. So let's do it. Multiply 1, 0, 0 by this column. I know this produces the same minus 1, no change here. This by the second column produce 2, no change. This first row by the third column produce 7, doesn't change anything. In the second row will be this by the second row, and again nothing changes. It will be this one multiplied this 2, the other will be multiplied by 0. So this will be the same thing, 2, then 0, and then minus 5. But if we multiply the third row by the matrix, this 2 will be multiplying this 4. The other products will be 0, but these 2 will be multiplying this 4. And this produces an A here. So these 2 multiply again this 4, so produce 8 here. These 2 multiply 6 here, minus 6 here, will produce a negative 12. So the third row was multiplied by 2. And if you you will notice that when you multiply the last row by all the columns, the answer doesn't change, the fourth row. So minus 3, 0, 9, and that will be again. So let's multiply the matrix A by E2 produces the same effect as the row operation 2R3. Substitute R3. So the R3 has been substituted by 2R3. So the third row was multiplied by 2. Exactly as was done in the identity by this elementary matrix. Finally, if we have this operation, this elementary matrix, you notice that this elementary matrix was the identity in which we have add to the first row 5 times the third row. So if we multiply this by this matrix, you are going to notice that will be 1, let's say first row, first column, 1 times negative 1, that will be negative 1. This 0, multiply this 2, it will be 0. This 5, multiply this 4. So it will be negative 1 the first, plus 5 times 4, so plus 20. So let's do it. It will be minus 1 plus 20. If we multiply first row, second column, so we'll have 1 times 2, 2. 0 times 0, 0. 5 times 4 is 20. So it will be 2 plus 20. And the other 0 multiplies 0, 0. So it will be 2 plus 20, the second element. When we multiply first row, third column, it will be 1 times 7, 7. 0 times negative 5, 0. 5 times negative 6, negative 30. So it will be 7 plus negative 30, or 7 negative 30. And the other row, there is no change. The answer will be 2. Because this 0 multiply this negative 1. The other 0 multiply this. This 1 is the only multiply this 2. So this 2 remains the same. When you multiply this by the others, so the answer will be the element in the second row. 2, 0, minus 5. And the same happens if we multiply this by all the columns. The answer will be 4 in the first one, 4 in the second one, because this one will be multiplying the third element in the column, that is 4. And then the last product will be this row, third row, multiplied by the last column. And the answer will be negative 6. And the same happens with when we multiply the fourth row multiplied by each of the column. The answer will be the last element in the column, minus 3, 0, 9. And that's gross. So we can make the operation here. But we notice that left multiplying the matrix A by E3 produces the same effect as the row operation. R1 plus 5 times R3, substitute R1. Exactly the same operation that was done in the identity to get this elementary matrix. So the answer, the other row doesn't change. This one is 19, this one is 22, and this one is negative 23. So this is the matrix obtained if we do that. So important here, making row operations is the same that multiplying by elementary matrices. And with this explanation, I finish this video. Thank you.